Greetings, Professor Walid, module moderator, and any other faculty staff present. As Team 8, we are proud to present to you our APM3715 Group Assignment Task C. Our approach to tackling the assignment was a very simple one. We would use given course content and material based on real-world civil engineering problems to provide an analysis and a solution to an existing problem. Our project is based off Learning Unit 1, Approximation and Rounding Off of Errors, and Numerical Integration, Learning Unit 5. As you will see in the presentation to come, we have selected a scenario which is best covered by the two learning units, Numerical Integration and Approximation of Rounding Off Errors. Our team had initially selected two scenarios on one given set of earth, one being a road design and secondly being a sewer network design. We have chosen the sewer network design as we believe that the skills and knowledge learned in this module are best demonstrated with this example. Our team started off with a number of 9 members, but due to unfortunate circumstances, our numbers have now dwindled down to 6. But nevertheless, with the efforts, contribution, and enthusiasm of the remaining members in the team, we have managed to complete the task very successfully, and the contributions from each member has resulted in a well-rounded, polished report. And we are proud to present to you the results of our shared learning experience.
Good day, everyone. You are speaking to N.Mashimbi. I'm going to present Task C. On this Task C, I'm going to present the introduction and the description of our problems, which for civil engineering problem. In the introduction is going to include the identification, the description of the civil problem, the aim of the task, graph details of the problem, the methodology for the numerical method, calculations, result by means of Simpson's rule, the GNU active result, conclusion, the purpose of a sewer system. So the next step is to describe the description of the civil engineering problem, which include a civil contractor was appointed to construct a new sewer line in the development. After a construction, the contractor claimed the quantity of 390 for a bulk excavation to install the sewer line. As Team 8, we have been tasked to confirm this quantity and report to the client if the civil contracts that stay within the 10% allowance for over excavation. Thank you.
Good day, my name is D.Mcleod and I will be presenting slide 4 and slide 5. The aim of this task shall be to use a numerical method learned during this course of this module that will be applied to this problem where a contractor has submitted a claim for excavation. The resident engineer will calculate the exact value of the total excavations by using a numerical method. Then it will be compared to the relative quantity claimed by the contractor. Keeping in mind the calculated quantity by the engineer shall be used as the exact value. The difference between the two shall be the percentage error, and this margin of error has been allowed for an overclaim of 0 to 10%. If this value is exceeded, the claim shall be deemed invalid. Moving on to slide 5 shows the graph with all the details. The red line indicating the existing ground level was obtained using survey data provided by a surveyor. A surface was created and existing ground levels were taken every 5 meter intervals to reduce the inaccuracy of the numerical method known as Simpson's rule, to obtain a slight accurate or slightly more accurate quantity of excavations. Therefore, 5-meter intervals were appropriate. The green line indicates the sewer inlet level, which was laid at the minimum and minimum slopes for adequate drainage. And the difference between the two shall be taken as the depth, which will be used to calculate the area using Simpson's rule. My contribution to the group was to design the sewer with the inlet levels to create a surface and to obtain all the existing ground levels at each interval, to lay the pipe according to cover levels and pipe IDs taken into account, and to tie into the existing manhole inlet level. This data was then used to obtain the depths, which I then used to calculate the Simpson's rule manually, and also I also used an online tool to confirm all the answers. Using the answers, the area was multiplied by the trench width to obtain the total volume.
My name is J.Schereneckau and I'll be presenting slides 6 and 7. I am part of Team 8 where my contributions were solving task A, B, and C, as well as chair and minute taker of meetings held with the team. Apology for the numerical problem. The team had a choice between numerous amounts of numerical methods, but through previous experiences we found that the Simpson's rule was more accurate and user-friendly. The Simpson's rule would then be used to calculate the material excavated by the contractor to determine whether or not the claim was valid for the material excavated. We used the Simpson's rule to calculate the excavated volume of 360.139, and this volume was calculated from chainage 0 to chainage 237.661. Compared to the claim from the contractor, where the contractor had an excavated volume of 390, this leaves a relative error of 8.29%. But even though the contractor's excavated volume is higher than the volume calculated using the Simpson's rule, we can still establish that the error is less than 10%. Therefore, the contractor can be paid out for the volume excavated. That would conclude my portion of the presentation. Please allow Camille to explain the octave programming required for task C.
Good day, my name is K.Mahomed. My student number is 537-80612. I'm a member of Team 8. As a member of Team 8, I contributed to a number of meetings and discussions around the development of our task C civil engineering problem, which we as a team were required to develop as part of this module's project. Part of my contribution was to lead the development of the GNU Octave script we would use as a team to solve our derived problem. The details of this problem, which my team would have covered in previous slides of our presentation. I will be focusing on slides 8 and 9, which cover the GNU Octave script and results, as well as the conclusion to our findings. As previously covered by my teammates, we use the Simpson's composite formula as part of solving our task using numerical methods, which we use to derive the area bounded between the surveyed ground levels and excavation levels of the sewer line trench. We then multiplied the derived area with the width of the trench to determine the excavated volume, which we then would compare against the contractor's claimed volume to determine if he was within the allowed margin of error. Using a CSV file containing the changes as well as the excavated depths, we imported this data into GNU Octave using CSV read command. As the overall length of the excavation could not be equally divided by the surveyed spacing of 5 meters, the approach taken in Octave was to determine the area between chainage 0 and chainage 235, thereafter determine the area between chainage 235 and chainage 237.661, and then sum these two values to get our total area under the curve. We would then multiply this total area by the trench width to give us our excavated volume. The results derived from the Octave script appears to be consistent with the results of both the manual calculations we had completed as a team, as well as the check we had done using online electronic resources available on the internet. The area between chainage 0 and chainage 235 was found to be approximately 396.9 square meters, and approximately 3.2 square meters between chainage 235 and chainage 237.661. This gave us a total area of approximately 400.1 square meters. Multiplying this total area by the trench width of 900 millimeters, we derived an excavated volume of approximately 360.14 cubic meters. In comparing this result to the contractor's claimed volume of 390 cubic meters, we determined the difference between the claimed volume and the calculated volume to be 29.86 cubic meters. This difference represents a margin of error of 8.29%. As this margin of error is within the allowed margin of 10% for over-excavation as stipulated by the cost controller, we as Team 8 have assessed the contractor's claim to be within the allowed margin of error. As such, we would recommend to the cost controller that the claim can be paid as submitted.
Good day, my name is G.Oosthuizen, student number 618755341. I am presenting the last slide of our presentation for Task C. This slide indicates a layout drawing of our proposed sewer system. It shows the sewer system starting at ERF 62 and continuing on, stopping at or besides ERF 1, where the last manhole will tie into the existing sewer system. This is the path of the trench excavations where we did our Task C for the bulk excavations to prove the contractor on his claimed excavation quantities. The sewer system chainage was from chainage 0 to chainage 235 and had a bulk excavation quantity of 360.139 cubic meters as calculated through our calculations.